Welcome to Math, Week 12, Rational Expressions. This is Module Math 1 on the Math Tutor Self-Study track. Today's lesson is 120 minutes with a 10-question practice quiz and a cumulative review covering weeks 9 through 11. This week we extend fraction arithmetic to fractions of polynomials. Same rules: cancel common factors, never common terms. Build a common denominator before adding. Flip the divisor before multiplying. This video is sponsored by Subthesis. Visit subthesis.com to learn more. A rational expression is a fraction whose numerator and denominator are polynomials. Like fractions of numbers, they simplify by canceling common factors, never common terms. That single discipline is the most important habit this week. Here is the agenda. We start with domain restrictions because the denominator can never be zero. We simplify by factoring and canceling, with the cancellation rule called out as the most common error in algebra. We multiply, divide, add, and subtract. The least common denominator method handles addition and subtraction. We close with Bayes' theorem, which is structurally a rational expression. Then quiz, recap, and a forward look at Lesson 13. The denominator of a rational expression cannot be zero. Always identify the values that would zero out the denominator and exclude them from the domain. Two quick examples. The fraction x plus 1 over x minus 2 has domain x not equal to 2. Anything else is fine. The fraction x plus 1 over the quantity x minus 3 times x plus 5 has domain x not equal to 3 and x not equal to negative 5. Both factors of the denominator must be non-zero. Crucial habit: state domain restrictions before you simplify. Why? Because once you cancel a factor, it is gone from the simplified expression, but the original equation was still undefined where that factor was zero. The restriction must travel with the simplified form. 3 steps to simplify. Factor numerator and denominator completely. Cancel common factors, meaning entire parenthesized expressions, not individual terms. State domain restrictions for any canceled factors so they are not lost. Worked example. Take x squared minus 9 over x squared plus 5x plus 6. Factor. The numerator becomes x minus 3 times x plus 3. The denominator becomes x plus 2 times x plus 3. Cancel the x plus 3. You get x minus 3 over x plus 2. State restrictions. X not equal to negative 3 from the canceled factor, and x not equal to negative 2 from the surviving one. The canceled x plus 3 does not appear in the simplified expression, but its restriction, x not equal to negative 3, survives. Do not drop it. Now let us multiply two rational expressions. Take x squared plus 2x over x squared plus 5x plus 6 times x plus 3 over x. Step 1. Factor everything. The first numerator factors as x times x plus 2. The first denominator factors as x plus 2 times x plus 3. The second fraction stays as x plus 3 over x. Step 2. Cancel. The x plus 2 appears in the first numerator and the first denominator, so cancel it. The x plus 3 appears in the first denominator and the second numerator, so cancel it. The x appears in the first numerator and the second denominator, so cancel it. Step 3. Everything has canceled. The result is 1. Restrictions. X not equal to negative 2, x not equal to negative 3, and x not equal to 0 from all the canceled factors. Now let us add two fractions with unlike denominators. Take 3 over x plus 1 plus 2 over x. Step 1. Identify the least common denominator. The denominators are x plus 1 and x. They share no common factors, so the least common denominator is x times the quantity x plus 1. Step 2. Rewrite each fraction over the least common denominator. The first fraction is missing a factor of x, so multiply its numerator and denominator by x. That gives 3x over x times x plus 1. The second fraction is missing a factor of x plus 1, so multiply its numerator and denominator by x plus 1. That gives 2 times x plus 1 over x times x plus 1. Step 3. Add the numerators. 3x plus 2x plus 2 over x times x plus 1. Combine like terms. 5x plus 2 over x times x plus 1. That is the final answer. Restrictions. X not equal to 0 and x not equal to negative 1. The most common error in algebra. You can cancel factors, things that are multiplied, but you can never cancel terms, things that are added or subtracted. Wrong. X plus 1 over x plus 2 does not equal 1/2. The x's are terms inside the parenthesized expressions, not factors. They cannot be canceled. Right. 2x times x over 3 times x equals 2x over 3. Here, the x's in numerator and denominator are factors, multiplied, and 1x cancels cleanly. Memorize this rule. Internalize it. Half the algebra mistakes in calculus trace back to violations of this single principle. The litmus test. Can you literally pull the symbol out as a factor of the entire numerator or denominator? If yes, cancel. If no, leave it alone. Multiplying rational expressions. Factor everything first. Multiply numerators together, multiply denominators together, then cancel any factor that appears in any numerator and any denominator. Cross-canceling is fine because everything is being multiplied. Dividing. Flip the second fraction, the divisor, the one after the division sign, and multiply. Never flip the first fraction. That is a common error. Worked example. X squared over x plus 1 divided by x over x plus 1. Flip the second fraction to get x plus 1 over x, then multiply. X squared times x plus 1 over x plus 1 times x. Cancel x plus 1 and one factor of x. What is left is x, with restrictions x not equal to negative 1 and x not equal to 0. Both restrictions survive because the original expression had x plus 1 in a denominator, and the second fraction had an x in its numerator that became a denominator after the flip. Adding and subtracting rational expressions follows the same rule as adding numerical fractions. A common denominator is required before the numerators can combine. There is no shortcut around this. If the denominators differ, you must rewrite both fractions over a shared denominator first. The systematic way to do that is the least common denominator method. 4 steps. Step 1. Factor every denominator completely. You cannot build a sensible least common denominator until you can see the prime building blocks of each denominator. Step 2. Build the least common denominator as the product of every distinct factor, each raised to the highest power it appears in any single denominator. If one denominator has x plus 1 and another has x plus 1 squared, the least common denominator takes x plus 1 squared. The higher power wins. If denominators contain unrelated factors, the least common denominator takes a copy of each. Step 3. Rewrite each fraction over the least common denominator by multiplying its numerator and denominator by whatever factors it is missing. Same factor on top and bottom is multiplying by 1, so the value of the fraction does not change, only its form. Step 4. Add or subtract the numerators, keep the least common denominator, and simplify. Worked example. Take 1 over x plus 1 plus 2 over x minus 1. Step 1. The denominators are already factored, x plus 1 and x minus 1, both linear and distinct. Step 2. The least common denominator is the quantity x plus 1 times the quantity x minus 1, one copy of each distinct factor. Step 3. Rewrite each fraction. The first one is missing x minus 1, so multiply numerator and denominator by x minus 1. It becomes x minus 1 over x plus 1 times x minus 1. The second is missing x plus 1, so multiply numerator and denominator by x plus 1. That gives 2 times x plus 1 over x plus 1 times x minus 1. Step 4. Add the numerators over the common denominator. X minus 1 plus 2 times x plus 1 all over x plus 1 times x minus 1. Distribute and combine. X minus 1 plus 2x plus 2 equals 3x plus 1. Final answer. 3x plus 1 over x plus 1 times x minus 1. 2 important habits. First, do not multiply out the least common denominator into a single polynomial unless you have a reason to. Keeping it in factored form makes it obvious whether the final answer reduces further by canceling. Second, after combining, check whether the new numerator shares a factor with the least common denominator. If it does, cancel and update the restrictions. In our example, 3x plus 1 does not share a factor with x plus 1 times x minus 1, so the answer is already in simplest form. A forward note. This least common denominator machinery is a prerequisite for next week's rational equations. Clearing denominators in something like 1 over x plus 1/2 equals 3/4 is exactly the same construction, just applied to both sides of an equal sign rather than across a single sum. The 4-step recipe you just learned generalizes directly. Let us work through a division example. Take x squared minus 4 over x plus 1 divided by x minus 2 over x plus 1. Step 1. Flip the second fraction. The divisor x minus 2 over x plus 1 becomes x plus 1 over x minus 2. Step 2. Multiply. X squared minus 4 over x plus 1 times x plus 1 over x minus 2. Factor x squared minus 4 as the quantity x minus 2 times the quantity x plus 2. Now we have x minus 2 times x plus 2 over x plus 1 times x plus 1 over x minus 2. Step 3. Cancel. The x plus 1 appears in both a denominator and a numerator, so cancel it. The x minus 2 appears in both a numerator and a denominator, so cancel it. What remains is x plus 2. The final answer is x plus 2, with restrictions x not equal to -1 and x not equal to 2 from the cancelled factors. Now let us tackle subtraction, where the negative sign creates a common trap. Take 2x plus 1 over x plus 4 minus x minus 3 over x plus 4. The denominators are already the same, so we can subtract the numerators directly. But here is where the trap lives. The subtraction sign must distribute across the entire second numerator, not just the first term. Step 1. Write the combined fraction. 2x plus 1 minus the quantity x minus 3 all over x plus 4. Notice the parentheses around x minus 3. They are essential. Step 2. Distribute the negative. 2x plus 1 minus x plus 3 all over x plus 4. The minus times the minus 3 gives plus 3. This is the sign trap. Many students write minus 3 instead of plus 3. Step 3. Combine like terms. 2x minus x is x. 1 plus 3 is 4. So we get x plus 4 over x plus 4. Step 4. Cancel. X plus 4 over x plus 4 equals 1, with the restriction x not equal to negative 4. The final answer is 1. Always use parentheses when subtracting rational expressions to protect against the sign trap. Bayes' theorem is structurally a rational expression. The probability of A given B equals the probability of B given A times the probability of A, all divided by the probability of B. The numerator is likelihood times prior. The denominator, the probability of B, is the evidence, a normalizing constant. The denominator is often hard to compute because it is an integral over all hypotheses. In many machine learning algorithms, such as naive Bayes and maximum a posteriori estimation, when the probability of B is independent of the parameter we are optimizing, we can drop it. It does not affect which value of the parameter maximizes the expression. That is the same cancel factors that do not depend on what we care about in tuition you just practiced on rational expressions, just transplanted into probability. Now let us check your understanding with a short practice quiz. 10 questions on domains, simplification, the cancellation rule, multiplying and dividing, and the Bayes connection. Pause after each prompt to think before I reveal the answer. Question 1. What is the domain restriction for the fraction x plus 1 over x minus 2? Take a moment to think about it. The answer is x not equal to 2. The denominator cannot be 0, and the denominator zeros at x equals 2. Distractor A reads the numerators 0, which is the wrong side trap. The numerator can be 0. That just means the function equals 0, not that it is undefined. Question 2. Simplify x squared minus 4 over x minus 2. Take a moment to think about it. The answer is x plus 2. The numerator is a difference of squares, x minus 2 times x plus 2. Cancel the common factor x minus 2. The simplified form is x plus 2, with the restriction x not equal to 2 from the cancelled factor. This drills the factor first habit. Question 3. Multiply x over 2 times 4 over x, assuming x is not equal to 0. Take a moment to think about it. The answer is 2. Cross-cancel the x's. They are factors of the numerator and denominator. Simplify 4 over 2 to get 2. Distractor C. 4 over 2 is the same value but unsimplified, which counts as wrong on a simplified form question. Distractor D ignores the cancellation entirely. Question 4. Simplify x squared minus 9 over x squared plus 5x plus 6. Use parentheses in your answer. Take a moment to think about it. The answer is the quantity x minus 3 over the quantity x plus 2. Factor. The numerator is a difference of squares, x minus 3 times x plus 3. The denominator factors as x plus 2 times x plus 3. Cancel the shared factor x plus 3. Restrictions. X not equal to negative 3 from the cancelled factor, and x not equal to negative 2 from the surviving denominator. This drills factor and cancel discipline. Question 5. Divide x squared over x plus 1 by x over x plus 1. Take a moment to think about it. The answer is x. Flip the second fraction, the divisor, to get x plus 1 over x. Then multiply. X squared times x plus 1 over x plus 1 times x. Cancel x plus 1 and one factor of x. What is left is x. Restrictions. X not equal to -1 and x not equal to 0. This drills the flip the second rule. Question 6. Common error to avoid. Can you cancel the x in the fraction x plus 1 over x plus 2? Take a moment to think about it. The answer is no. You cannot cancel because terms are not factors. The x inside x plus 1 is added to 1, not multiplied. Same for the bottom. Cancellation is only legal across multiplication. This is the cancel across addition trap that defines this entire lesson. Question 7. Bayes' theorem is structurally what type of mathematical object? Take a moment to think about it. The answer is a rational expression. The probability of A given B equals the probability of B given A times the probability of A, all divided by the probability of B. A polynomial-like quantity over another polynomial-like quantity. Posterior equals likelihood times prior, all divided by evidence. That is a rational expression in form. Question 8. Simplify 2x plus 6 over 4. Take a moment to think about it. The answer is x plus 3 over 2. Factor 2 from the numerator. 2 times the quantity x plus 3 over 4. Reduce 2 over 4 to 1 over 2. That is a constant factor, so it is legal to cancel. Final answer, x plus 3 over 2. No domain restrictions because the denominator is a non-zero constant. This drills the factor out the greatest common factor habit. Question 9. What is the domain of the fraction x plus 1 over the quantity x minus 3 times x plus 5? Take a moment to think about it. The answer is x not equal to 3 and x not equal to -5. Set each denominator factor to 0. X minus 3 equals 0 gives x equals 3. X plus 5 equals 0 gives x equals -5. These are the excluded values. Distractor D mistakenly includes x equals -1, the numerator 0, but a 0 numerator just means the function equals 0, not that it is undefined. The all 3 distractor is the exclude every 0 trap. Question 10, a reflection question. Why does Bayes' theorem look like a rational expression, and why does that matter for machine learning? Take a moment to think about it. Bayes' theorem equals the probability of B given A times the probability of A, all divided by the probability of B. The denominator, the marginal, is often hard to compute because it is an integral over all hypotheses. In many machine learning algorithms like naive Bayes and maximum a posteriori estimation, we cancel or simplify the denominator using the same rules you just practiced on rational expressions. When the denominator is independent of the parameter we are optimizing, we can drop it entirely. That is why maximum a posteriori estimates work so smoothly. The cancel common factors rule is also why log posterior maximization works. The dropped constant becomes a dropped additive constant after the logarithm. Quick recap. You factored numerators and denominators of rational expressions, identified domain restrictions before any cancellation, multiplied and divided them by leveraging factoring plus cancellation of common factors, and added and subtracted them via the least common denominator method. The discipline of never canceling across addition, only across multiplication, is the single most important habit to internalize here. 3 trap families fell: the cancel across addition trap, where students treat terms like factors; the drop the restriction trap, where canceled denominators stop imposing domain limits; and the flip the wrong fraction trap, where students invert the dividend instead of the divisor. The cumulative review reinforced factoring, vertex form, completing the square, and the 4 quadratic solving methods from weeks 9 through 11. Coming up next. Next week solves equations that contain rational expressions, where extraneous solutions can sneak in when you multiply through by a variable expression. You will learn to clear denominators with the least common denominator, solve the resulting polynomial equation, and verify each candidate against the original domain. The verify the domain habit transfers directly to numerical stability concerns in machine learning training loops, where division by near zero values causes silent bugs. That wraps up this week's lesson. Thanks for watching. If this helped, please like and subscribe. It tells the algorithm to put this in front of more learners. See you next week.